interesting detour. Let's talk about this last section, which is kind of short. There's not a ton of problems on it. It's mostly telling you some other types of graphs other than the histogram, and how you can also deceive people with graph, right? Maybe you've ever taken a class on lying with statistics. So, right, we're going to do this histogram from the data more later, right? I'll show you how to do that using, you can do it by hand, right? So it's really easy to do by hand. You do the frequency distribution, and you can draw the bars, right? The technology is good for that, right? It's going to be more accurate. So I'll show you how to do that in our video that I'll assign you. Let's look at some other types. So one type of data, the data is dot plot. So each dot represents people, and right? Pulse rate, and then there is one individual with a pulse rate 102. Someone here with far right, where two people have a pulse rate, right? If you think about this, this is very similar to a histogram, and technically it is. So this is technically, except other than using points, this is really a histogram. What would be the class size for this histogram? Would be, so if these both represent 50, not 51 and 49, the class size of 1, if you think about it, right? Because the only the only things that are in the same bar are data values that have the same integer values, right? So dot plot, looking at the broken, you can have histogram class size 1. You can have class size 0.1, right? So dot plot's very similar to a histogram. They're nice because they show you the distributions, right? But it's also nice because it's usually possible to recreate, right? When you do a histogram, and I say I have 5 values between 10 and 15. No exact value. How many of those are 10? How many of those are 5? If you make histogram from your data, if you create your data exactly, you can, because each dot represents 1 point and it's only over the exact number that it is, right? So you can recreate your data. That's something that's nice about these. Another example, has anyone seen a seven-leaf plot before? Maybe? Okay, some of you have, right? But it's pretty similar to histogram. Yeah, none of these graphs, so these graphs right now you want to use to represent quantitative data, so not nominal data, right? Remember nominal or ordinal would be tricky TV, right? But definitely interval and ratio. And so seven-leaf plot, right? Each tens or sometimes tens and hundreds place, right? It's represented on the left, and then you otherwise just organize your value in order, right? So here you can see that there's one individual with a pulse rate of 48 over 42, and 1, 2, 3, 4, 5 with a pulse rate, right? And you can kind of see a little bit of the distribution here too. So this is roughly normal, but it looks like it's kind of skewed to the right. Does everyone see that? Imagine turning this thing sideways, right? Then you would see them skewed to the right. The average is somewhere in that 60s, but there is a lot more that's big there, right? So notice this is the same data as this one over here. We definitely see skewed to the right, although it's not as clear that it's normal. It might not be. Anything on you? You can also maybe notice other things in the stem and leaf plot that you may have not noticed in the previous chart. What is strange about this? They're all something that you wouldn't expect. Hear somebody say, I think they said it correctly, say it louder. They're even, right? Why would they all be even? Why does no one have an odd pulse rate? Oh, multiplied by 4. What happens here is they're all even, and there's some that are not all 4. If they count how many beats they pop, if they count beats for 30 seconds, and so that's a bit tricky. I'm going to have to back up. Does everyone see how a procedure counts how many you get pretty fast? All something that looks like this, right? You can have putting down the half. So again, shows the shape of the data, retains the digital data values, and it sorts the data. So that's something that's useful. So these are good at just representing certain types of numerical values, right? Now here, you might have data, but the data is collected at different times, right? What's the temperature outside at 10 in the morning, 11 in the morning, noon, right? Then you would maybe want something like this, where you would have, notice each data, right? Piece of data is really a pair of data. So that looks like it might be 1988 and 195, right? So you have a piece of time, right? Each data is paired, and you want to pair the time. So you want to have it on, instead of something one-dimensional, you want to have two-dimensional graph. You can see outliers. Are there any outliers? So we see a trend generally decreasing law enforcement fatalities from year to year, although not consistently decreasing. Does anyone see an outlier here? One like up there, yeah, you see it. Any thought about what this might be? Law enforcement fatalities in that year, yes. There was an event. Does anyone know what event that is? Look at where it is on the time scale. Yeah, that was 2001 because what happened in 2001? 9/11, those are all the brave policemen who went to the Pentagon and the that's why like, interesting patterns by looking at graphs. You can see that, right? Maybe if I'm wanting to look at a trend, maybe I want to take that out of my analysis since that's kind of a singular event, right? Because I'm sure most of these other law enforcement fatalities are not like that. And actually, most law enforcement fatalities are not what you think. Most law enforcement fatalities are not shootings or attacks. They are, you want to know what the most cause of law enforcement deaths on the job is? Yeah. Car accidents, and particularly, and this is something I've always seen. I've been speeding, right? You pull me over for speeding. Someone else is not paying attention, drifts me in the shoulder. That's the most common way that is actually the most dangerous things that police officers do in a speed stop. Is not that someone will start shooting at you, but that someone will hit you their car, right? Or that can also happen to tow truck drivers. Fortunately, there was one that happened near my house about a year ago. The tow truck driver was about your age, and the teenager wasn't paying attention. So be careful when you're a pedestrian, right? Because the cars are a lot. Okay, that was sad. Let's talk about fruits. That's happy, right? So this is a bar graph. Okay, awkward transition. There we go. So this is different than a histogram in that data on the bottom is nominal, non-numeric, right? So unlike a histogram, you can look at trends, right? Speed, right? People form. I guess you use this. You can't describe things. The ordering of the groups on the bottom are arbitrary, right? So the difference between the bar graph and the histogram is that the histogram is for numerical data, right? So ordinal dating, but probably numerical spacing data. While the bar graph is not looking trend going left to right because the ordering of the fruits is arbitrary, right? Right. I was asking my last class. Are this many people really down on bananas? Is anyone in this class your favorite fruit a banana? No, okay, maybe you, maybe. All right, so maybe, but grapes is really not popular. Grapes, yeah. I mean, they're annoying to pull all of them off, right? And they clean them, and there's always a couple of bad ones, and you keep the stem. A lot of people like grape flavor. Is it just me or does grape flavor, like in soft drinks, gum, not really taste like grapes? No, I'm with you. I don't think there's anything from grapes that's in those things. It's just purple. Okay, so this is a bar graph. A special type of bar graph is called a Pareto chart. Pareto chart is a bar graph for nominal data, but you just organize it from greatest to least, right? Just so you can kind of see what categories are the most common, what are the least common, right? So a Pareto uses the fact that the nominal order is arbitrary and orders it by category by, right? So again, some people like, oh, right, no, you can't see the range of categories. Then it helps to see, right, what things are the most categories the most common, right? I think this is what you and you can see what it's expect. These are different types of boats. What are stolen the most? Jet skis make that. They're very fast, so if you can steal it, you can make a quick getaway, and you can probably hide it in the back of a van or a moving truck. I don't know. That looks like maybe 25 stolen sailboats. I would like to watch that happen. The police come after you. What do you do if it's not windy? I don't know. You just kind of stay there. That's probably why us didn't. I like to. Well, let's see. I like to see the Pareto chart for attempts, right? Maybe there. I like to see. Yeah, that would probably be different. I don't know. I never heard. When I was a freshman in college, my roommate was big into sailing, and he invited me once. And I said, "Sure, let's go." And he's like, "All right, I'll see you on Saturday at 5 in the morning." I said, "Yeah, I'm not going. That's too early to get up on Saturday." The pie charts are very similar to bar graphs, except it shows them as a proportion of a whole, right? This is the same thing. Oftentimes, the pie chart, they also kind of do the Pareto chart method and organize it from least to greatest, either clockwise or counterclockwise. Doesn't really matter. Let's know. Does anyone know what an inboard boat is? Nautically inclined. Oh, nobody here knows. Yeah, I thought we might know. I guess this is South Chicago. Maybe if we were up north, we're closer to the lake, someone might know, right? No one knows. I live in Champaign. No one knows about any boats there. We don't have any lakes, rivers. We got nothing. Okay. How do you lie with graphs? Well, we're not. I mean, one, you could just make up the data, but how do you more deceive somebody with a graph? So, one, you want to not have. Thank you for listening all this time. I'll be over very soon, I promise. Right? You want to carefully see whether the vertical axis begins at another point than zero, right? So look, this makes this oxycontin seem to have a giant effect on the notch, right? But if you have ratio data where there is a particular 0 point, it doesn't make sense, right? When you look at this, okay, it's twice as large, right? But here, starting at 10%, it makes it look like it's much greater. Perhaps you've seen this trick before, right? So bar graphs are misleading, or if 0 is not the start of the bar. Another one is pictographs, right? If you ever look at the magazine USA Today, not magazine's newspaper, not one that's very popular now, right? They have a lot of pictograms. So data that's one-dimensional in nature, such as a numerical amount, right, a percentage, if it's represented by an object that's two-dimensional, it can mislead you, right? Because I'll show you what this means in a second, right? That's just basic geometry. This square is twice as big in both its length and its width, but it's 4 times as much, right? So if this represents a quantity that's 2 times, but the picture is 4 times, it exaggerates the difference, right? And if it's depicting a 3-dimensional object, that's even more, it's 8 times. So let's kind of see what I'm saying here, right? I think you can see with this picture. So, there, goodness, don't smoke, it's not good for you, right? 1970, 37%, about $30. 2013, less than 1/5, right? That's the difference. But this exaggerates, right? This first cigarette is twice as long, but it's also something that looks the same, twice as wide. And with the perspective, right, it's twice that big in the book. So it looks 8 times as big, right? But it's really twice for diagram. That would see how, right? Visual aspect. Really should all be. They could do this. If they want to do this, the cigarette should be the same, right? But it's very long, right? You make it the same. It's going to double everything. Same thing here, right? This is supposed to represent a fair. It's supposed to be $1. Multiply 50 by itself, you get something around 6.25. Again, it is exaggerating the difference, right? This looks more than 2.5 times larger. So in general, what's the rule? 20 values or less, table, it's better than a graph. Graph should focus on the nature of the data, not design elements. Don't distort. And most of the ink should be used for the data, not other design elements.